Today we are looking at EgoScale, scaling dexterous manipulation with diverse egocentric human data.
This is a really fascinating collaboration coming out of NVIDIA, UC Berkeley, and the University of Maryland.
Let's get right into the 60-second summary. The big idea here is tackling the massive data bottleneck in robotic dexterous manipulation. They did this by pre-training on an absolute massive scale.
Exactly. We are talking 20,854 hours of egocentric human video.
Which led to their key finding. They uncovered a pristine log-linear scaling law. Basically, as human data volume increases, validation loss drops predictably, and this actually correlates to real-world robot performance.
The methodology is a two-stage process. First, that massive human pre-training, followed by a very lightweight mid-training phase using aligned human-robot data.
And the results speak for themselves. A 54% improvement in success rates over the baselines. It proved capable of one-shot generalization on complex tasks like shirt folding.
And it showed valid transfer across entirely different robot embodiments, going from a 22-degree of freedom hand to a tri-finger hand.
All right, welcome to AI Paper Podcasts. So I want to transition to the deep dive on this because, well, for you listening, if you've been tracking AI for the last couple of years, you know the story of LLMs.
Right, the bitter lesson.
Exactly. The formula was deceptively simple. You take a transformer architecture, feed it internet-scale text, and boom, emergent intelligence. But for physical intelligence, for robotics, we've been totally stuck.
We have, because in robotics, specifically with dexterous manipulation, that internet-scale data just doesn't exist. You can't scrape the physical world.
Right. You can't just download a data set of a robot folding laundry. The traditional way is teleoperation, right?
Yeah, teleoperation, which is literally a human operator remotely puppeting a robot to teach it what to do. It is incredibly slow.
And it doesn't scale. If you want 10,000 hours of data, you have to pay a human to sit there for 10,000 hours.
And it's exhausting work. It's expensive, and honestly, we just hit a wall with it. Which is why we see Boston Dynamics robots doing backflips, which is largely a control theory and physics problem. But a robot struggles to just, sort objects in a bin.
Semantic manipulation is just a different beast.
Yeah.
So the authors of EgoScale basically said, let's stop trying to manually generate robot data. Let's just use the human data that's already everywhere.
Right. Humans are the ultimate scalable source of manipulation data. So they pulled together over 20,000 hours of egocentric video.
First-person video, like GoPro footage.
Exactly. And just to put that 20,000 hours into perspective for you, most of the imitation learning papers we see use maybe tens of hours of data.
Maybe a few hundred if it's a massive lab.
Yeah, exactly. A few hundred. So 20,000 hours is roughly a 20x jump in scale over previous state-of-the-art data sets. It is an order of magnitude shift.
And they deliberately chose egocentric data, which solves a huge problem in robotics vision, the occlusion problem.
Yes, occlusion is a nightmare. If you train on third-person video, like a camera sitting on a tripod watching a human, the human's arm or body will constantly block the view of the finger.
You can't see the grasp.
Right. But with a head-mounted camera, the camera is basically the eyes. You get the exact approach vector, the micro adjustments of the thumb, the exact point of contact.
And the diversity of this data set is wild. They didn't just film a lab. The paper mentions they covered nearly 10,000 distinct scenes and over 43,000 unique objects.
It's totally in the wild footage. Retail repair services, people cooking in their actual kitchens, construction sites.
So they take this absolute mountain of noisy, chaotic human data, and they find what I think is the biggest aha moment in the entire paper, the scaling law.
Figure 5.
Yes, figure 5. If you're an ML engineer, this is the chart that's going to keep you up at night. They train their models on subsets of the data, 1,000, 2,000, 4,000, 10,000, and the full 20,000 hours.
And what they found was a perfect log-linear relationship.
It's beautiful. The equation they mapped out is L equals 0.024 minus 0.003 times the natural log of D.
Where L is your validation loss and D is the data set size.
And why that equation matters so much to you listening is that it implies no saturation.
Exactly. The graph doesn't flatten out.
It just keeps dropping.
Right. Which means if we just keep feeding it more human video, the robot's understanding of manipulation is just going to keep getting better. It turns a massive scientific mystery into a predictable engineering problem. Add compute, add data, get better robots.
But I do want to play devil's advocate here because in the sim to real world, Offline validation loss is sometimes a totally fake metric.
Oh, absolutely. It was the classic trap.
Right, like your model gets really good at predicting the next frame of a video of a hand grabbing a mug. Low loss. But then you put that on a physical robot and the robot just smashes the mug into the table.
Because predicting pixels isn't the same as applying torque. But this is where the EgoScale team really did their homework. They ran the correlation analysis.
And it held up.
It did. The offline validation loss on the human video directly and strongly predicted how well the physical robot actually performed the tasks.
Which is wild. It basically proves that if you get better at predicting human motion, you inherently get better at robot motion.
It suggests there is this shared underlying physics of manipulation, a foundational motor prior that works whether you're using biological muscles or electric actuators.
Okay, so let's get into the technical deep dive on how they actually bridge that gap. Because a fleshy human hand with skin fiction is fundamentally different from the Galaxy robot hand they used.
Yeah, a metal hand with motors. You can't just wire a YouTube video directly into a PID controller.
So they built the EgoScale framework to translate this, and they tackle the arm and the fingers as two separate problems. Let's start with the wrist motion, which is basically the arm's trajectory.
The biggest challenge with egocentric video is camera movement. Right. If I'm wearing a GoPro and I lean my torso forward, the camera moves closer to my hand. If you feed that raw data to a robot, the robot might think the hand is moving backward relative to the body.
Which would cause the robot arm to jerk erratically.
Exactly. So to fix this, they use the relative wrist motion between frames. They calculate it in SE3 space, the special Euclidean group that covers 3D rotation and translation.
So they're looking at the delta.
Yes, the delta between time step t and time step t+1. By only looking at the change in position relative to the camera, the movement becomes completely invariant to whatever the human's head or body is doing.
That isolates the pure manipulation action. So that solves the arm. But the fingers seem infinitely harder. You've got to map a human hand to a 22 degree of freedom mechanical sharp hand.
It is much harder. They use an optimization-based retargeting algorithm for this.
Yeah.
First, they extract 21 human hand key points from the video.
The knuckles, the fingertips, the wrist.
Yeah. Then they have to map those points to the robot's specific joint space. But human video tracking is notoriously noisy. It jitters.
Oh yeah, if you fed that raw jitter into a robot hand, the motors would just violently vibrate and burn out.
Exactly. So the optimization algorithm enforces strict robot joint limits. It essentially asks, what is the physical configuration of this robot hand that most closely matches the human hand key points without breaking the robot?
And they apply smoothing to filter out that temporal jitter. So the output of all this pipeline is a massive, clean data set of robot-compatible actions derived entirely from human video.
Which leads us to the model architecture itself. They use a vision language action model of VLA.
Built on a diffusion transformer.
A DIT, yeah. We are seeing diffusion transformers everywhere now.
They're completely taking over.
They are. Here, the DIT acts as the action expert. You feed it the current RGB camera observation from the robot, plus a text instruction like, iron the t-shirt.
And it generates the trajectory.
Right. But because it's a diffusion model, it starts with pure noise and iteratively refines it into a smooth, clean trajectory of actions.
It's planning a fluid motion instead of just jerky step-by-step predictions. So they have this incredible model trained on 20,000 hours of human data. But, and the authors are very upfront about this, if you just take that model and run it on the robot,
it fails.
The zero-shot transfer directly from human video to the robot is still too hard.
The embodiment gap is just too wide. The model has learned the general concept. It knows it needs to approach the cup, close the fingers, and lift, but it doesn't know the microphysics of its own metal body.
Right. It doesn't know the exact torque curve of its motors or how slippery its own metal fingertips are compared to human skin. So to cross this gap, they introduce a second stage called mid-training.
This is the bridge to reality. They collected a small, highly aligned data set of play data.
And the ratio here is it blows my mind. After 20,000 hours of pre-training, the mid-training dataset is just 50 hours of human play and only 4 hours of actual robot teleoperation.
4 hours of robot data. That is nothing in the grand scheme of things.
But it's aligned data, right?
Yes. They had humans and robots doing similar generic manipulation tasks, just playing around with objects in perfectly matched tabletop scenes.
Same tables, same lighting, same objects.
Exactly. And what this does is ground those massive general features learned from the internet video into the specific control space of that exact robot hardware.
It acts as a translation layer. It tells the model, hey, remember all that physics you learned from retail and construction videos? Here is how that translates to these specific 22 motors.
And it absolutely works. The human pre-training alone was mediocre on the robot, but human pre-training plus mid-training was a massive winner. They saw a 55% improvement in task completion compared to a baseline that was trained from scratch.
Which brings us to the real-world experiments. Because they didn't just test this on picking up blocks, they used a Galaxia R1 Pro humanoid torso with 2 arms and those 22 DoF hands and give it some really gnarly tasks.
Really hard tasks, like shirt rolling.
Which involves a deformable object.
Deformable objects are the final boss of robotic manipulation.
Yeah, they are.
Because the state space is infinite. When you touch a fabric, it wrinkles, it folds, it collapses unpredictably. You can't model that with classic rigid body physics. The robot needs an intuitive understanding of the material.
They also did card sorting, which requires crazy high precision.
Right. You have to push down with exactly enough friction to slide one card off a deck without pushing so hard you move the whole deck.
And bottle unscrewing, syringe injection.
Yeah.
But the absolute craziest part of the paper, the thing that proves this really works, is the one-shot generalization.
This was the jaw-drop moment for me.
So they took the Roddle, which had seen shirt rolling during mid-training, and they gave it a totally new task: fold the shirt.
Now, folding is mechanically very different from rolling. Different pinch points, different trajectories. The robot had never folded a shirt in its life.
Never. So what do?
They gave the system literally a single video demonstration of a human folding a shirt.
One human video. And the robot just did it.
With an 88% success rate.
88%. With one human demo. Usually in robotics, one shot means we tried it 50 times and it worked once, so we filmed it.
Right, the classic cherry-pick video. But 88% is robust. It's deployable.
What does that actually mean for the model's understanding?
It proves the model has internalized a true motor prior. It isn't just memorizing specific joint angles for specific tasks. It understands the physics of fabric and gravity.
So when it sees the human fold the shirt once, it's not trying to copy the exact pixels. It's translating the intent of the human into its own physical understanding of the world.
Exactly. It's a conceptual mapping, which perfectly tees up their cross-embodiment experiments.
Because if the knowledge is truly conceptual, it shouldn't matter what body the robot has.
Right. So they decided to test this human-trained brain on a completely different body. They used the Unitree G1 robot.
Which is very different from the Galaxia.
Totally different. The G1 has a 7-degree of freedom arm and a tri-finger hand. It's essentially a 3-pronged claw. It looks absolutely nothing like a human hand.
You can't map 21 human key points to a 3-fingered claw one-to-one.
You can't. But because the core model learned a general embodiment agnostic understanding of physics from all that human video, they were able to transfer it.
And the results held up.
Oh, yeah. The policy pre-trained on the human data achieved over a 30% absolute improvement on the G1 compared to a baseline that didn't have the human pre-training.
Over 30% just from having watched humans.
Yes. The knowledge extracted from the human video is fundamentally hardware agnostic.
That is massive for the industry. It means that every time a robotics startup builds a new hardware platform, a new arm, a new gripper, they don't have to start collecting data from zero.
I can just download the EgoScale weights as their foundation.
It's the ImageNet moment for physical manipulation. So let's look at the future outlook. The authors wrap up by pointing out that this is just the beginning of the scaling curve.
Right, because all 20,000 hours used in EgoScale were labeled. They use off-the-shelf pose estimators to track the hands. But they point out that combining this with self-supervised learning on unlabeled video is the next frontier.
And there are billions of hours of unlabeled human video on the internet. Every DIY tutorial, every cooking show, every GoPro ski video.
If the log linear scaling law holds, and we have no reason to think it won't, and we tap into millions of hours of raw YouTube footage,
the performance ceiling is going to shatter. Which leaves us with this incredible, somewhat provocative thought for you to chew on. If robots can extract physical laws from pixels, Are we approaching a moment where a robot can learn any physical skill simply by watching a YouTube tutorial of us doing it?
Just like a human does. You watch a video on how to fix a sink, and you go do it.
Yeah.
The robot watches the same video, downloads the motor prior, and fixes the sink.
The data bottleneck is officially broken. Humans are the data. That wraps up our deep dive into EgoScale. If you found this breakdown of the scaling laws of physical intelligence valuable, make sure you subscribe to AI Paper Podcasts. We'll be bringing you more of the cutting edge every week. Thanks for listening.
See you next time.